puzzled by this. Right? Surprisingly, though, something that's thought outside the box and used the principle flow to achieve this. It was interesting because I didn't expect it. Anyway, the fuel to air ratio, that's what we need. And I've given some inlet conditions and outlet conditions. So people thought, okay, some solved it saying, well, this is the Rayleigh flow heat addition problem. So if I get my stagnation temperature inlet, get my stagnation temperature outlet, I could get my Q. Oh, well, I already have my Q. Why am I trying to find out? What did they do? I don't remember.
Q fuel over Q air.
But you already have Q. So what did they get? Big other question.
Does Rayleigh flow apply because this flow has heat addition and friction?
Yeah.
That's a good point.
The friction is not
That's absolutely correct. And that's why you need the conservation of energy, the way I solve it. So you're absolutely correct. So in reality, the solution, so let me go over the solution, the right correct solution first. Right here. So this is the right correct solution. Right there.
Correct.
I don't know why it's- Is that better? So this is the correct way of solving it. Saying, well, what do I know from my equations from reacting mixtures, right? Q is equal to the fuel flow multiplied by heat of combustion. I already know that as a fact. And I know that if I multiply my mass of air, multiplied by my fuel to air ratio, multiplied by heat combustion, which is right here. So this is fuel air ratio multiplied by m.1, which is mass of air, which I already got right here, multiplied by heat combustion. So I already know this because he's given it to me, 40,000 kilojoules per kilogram. And m dot, I already have it. So all I need is Q in. Oh, that's what I needed Q in. Q in and fuel to air ratio. So I'm trying to find F. So I need, from this equation, what do I have as my inputs or known values? Well, I have heat of combustion. This is known. This is known. This is unknown, and this is unknown. So I need to know Q in to figure out fuel air ratio. So how do I get Q in? Now, the truth is, and that's what your colleague just mentioned, if there is friction, you have to account for it. So what you're going to do is apply your conservation of energy. So your first law of thermodynamics. First law of thermodynamics, Q in is equal to m dot H2, the enthalpy, the static enthalpy, plus the kinetic energy. And that's what you get as the representation of the equation itself. And this is what you get as Q in. Once you know Q in, you substitute it in there, and you get your fuel air ratio. Now, as I said, some people say, well, it's a heat addition problem. I'm just going to take my stagnation temperatures and take a delta T. I think they got a very close answer. I think they got a very, very close answer. So I think primarily, like your colleague mentioned, it doesn't count for friction, but they, by doing that, they got a close value relative to the friction-based problem. Make sense? Any questions on this? Question?
For the second part, if you forgot to account for pressure drop,
Pressure drag, what do you mean? The force?
force,
Well, each one is independent.
because the whole equation is m dot u1 minus u2
Yes.
plus the pressure drag. So if we didn't account for the pressure drag, we just used the mass flow rate and the velocities. Using the
Pressure drag.
Yeah, you will get partial credit, but you didn't write the equation right. You didn't do the momentum balance correctly. So that you look at, I don't know, I'm not grading it, but maybe I could have broke it up more, but I mean, this should have been, you do have a pressure difference, right, which on the control body. So it's like saying, I'm gonna ignore this delta T. And you shouldn't really have ignored it, because it's given to you as a delta P already. So, but you will get partial credit for it, not before. But partial credit, yes. The fact that you thought of conservation of momentum. All right?
It's about the counts.
But keep in mind is, yeah, I mean, it's a small percentage overall. But anyway, any question on this? It's not as hard as we thought it would be in the exam. No, you got the right answer. No. So if you got the right answer using a different method, no, that's essential. Actually, I like the fact that you thought out of the box to solve it.
I gotta make be careful. She knows Michelle.
Yeah, you solved with the Rayleigh flow, and it came out close. I just don't remember the number. It came out close. You might not. I think there was a difference slightly, but you might use like 1 point or half a point or something like that. Okay. Question? We're good. Look, notice that the final answers are almost nothing in terms of the numbers. It's the equations that are really counting for most of the grade. Final answer is just a number at the end. Oh,
Sorry, Michelle.
right here. Final answers are smaller percentage relative to the equations itself. Okay? Any questions on this? Turned out easier than what we thought? Okay. So we overcomplicated things, like problem 1B. I think everybody overcomplicated this. The iterated method. I said I'm not going to get the iterated method. You would have flamed me if I gave you an iterated method. He said no iterative methods. Why is it bringing iterative methods? That should have been a red flag saying, no, something I'm doing is not right. Okay. This is in your bag. This, I don't know. Why would people get it wrong? I'm not saying that people did get it wrong. I think most actually got it right. And we still grading it, so I don't know. We haven't counted up the whole grade and all that, but you expected this problem in the exam. Who here was not expecting this? Raise your hand. Everybody was not expecting a vacuum mixture problem?
Just something you like. Who wasn't? What?
What's different about it? I think
What?
the homework problem. I think
You tripped.
Still
going.
So, what else?
Oh no! Hey,
No, that was close. Still recording.
well,
You didn't expect it, right?
Yeah.
hand me my charger.
I didn't even give you a lower. Oh, you're
What?
being sarcastic? So, it's an equivalence ratio of 1, right? So it's
Perfect
even
stoic.
simpler than the homeworks.
I know.
Homework you have to do 0.8 or something or higher. You have to do all these different gymnastics at homework. But for this, it's an equivalence ratio of 1. It's straightforward. Last year, I
Yo,
gave
hold
them this, and they struggled with trying to figure the molecular weight for this fuel composition. I'm giving it to you this year because I realize that might be an issue. And even for oxygen and nitrogen and everything, so we need molecular weights already. So this is a straightforward problem in terms of I have some fuel which looks awkward, right? It's ethanol. And it's oxygenated fuel. Looks awkward, but I already wrote it in a regular form for you, which is C2H6O. All you gotta do is keep your moles, number of moles. That's all you gotta do. Write it in the equation, like we did. You don't have to write it in this form, you can write it in that form to make it simpler. And all you got is an extra oxygen there. Now in the homeworks, you did CO, and you did CO2 reaction. So you're already familiar with the fact that you're not always gonna get CH4, for example, or H2O, H2 as a fuel. Here you got a ethanol-based fuel. So all you gotta do is put a constant right here, put a constant right here, put a constant right here, put a constant right here. Now let's tally up what we're putting in versus what reacts. So you do that, the same exact process that you've done in the homeworks, the same exact process that we've done in the class examples. You do it this way and you get your balance. It's straightforward. I got 2 moles of C. So I got 2 moles of C on the other end. I get my D. I get my B. I get my E. And that's it. This is my new balanced equation. That's all it is. It's straightforward. I think most got this. Now, you have to compute, what was the question? The fuel to air ratio for stoichiometric combustion. That's all it is. And I'm even giving you the percentages of oxygen and nitrogen, which I would have expected you to know this by now. So last year I didn't even give them that. But anyway, so we need the fuel to air ratio. Well, fuel to air ratio, I just need my mass difference, and we've done it many times. So once I know already a number of moles, I can figure out the number of fuel moles I have. Knowing the molecular weight, I can get my mass, and this is the fuel air ratio that I got for ethanol. So straightforward. That's right away 10 points in your pocket. Now, the next question was, find the heat of combustion at 25C. So I'm already telling you that it's at standard temperature and pressure conditions. So by doing that, and find the heat of combustion. You write down the big long equation that we did for heat of combustion, which you get Q for. Q is equal to the different enthalpy summations multiplied by their mole fractions. And obviously some of them are in elemental form, like nitrogen and oxygen cancels, nitrogen cancels. So all you gotta do is H2O, CO2, and your fuel. That's it. And once you put that, you get Q. Once you got Q, you already have the amount of mass of fuel that you had. So you just take the division, which is, where did we just write this equation again? Problem 2. You wrote this in problem 2. Am I showing it? Right here, this equation. It's exactly, where's problem 2? Right here. Or right here. So you're double dipping with your grades, by the way. The same equations. But anyway, you got this, then you need to get your heat combustion in terms of kilojoules per kilograms, which if you already know your the mass for the fuel, which you already got from the first problem, then you got your heat combustion. That's it, that's stoichiometric condition. Now, the last problem, the molecular weight of combustion products, that's a very easy one. That's a freebie. You don't even need to do any of this to do this. All it is, sum your number of moles and take the division of the number of moles you have relative to the total. So you get your mole fraction for H2O, mole fraction for CO2, and mole fraction for nitrogen, because these are your products. Then MW total is equal to the sum of the mole fraction multiplied by the molecular weight for each. So that's it. You already got your mole fractions multiplied by the molecular weight, which I gave you on the table. You get your molecular weight total. So straightforward. It's one of the example problems we've done, as well as in homework number 2 for this one. So this is actually homework 2. Without any reactive mixtures or anything. So this is actually gas mixtures. Without any reactions. Okay, question?
Did it say per unit mass, or did you do it per mole?
It did say per kilograms. Kilograms fuel.
Yeah.
And the reason we want to get used to the kilograms fuel, because in the end you're going to apply it to determine downstream and the propulsion system in general, so you want to have that kilograms per fuel, because in the end, yeah, you're computing everything in moles frame, but then you go back to the kilograms for the propulsion system. So you want to get used to doing that in general. Now, this problem, it's going to be
Disgusting.
2-minute solution for you once we actually start doing the propulsion systems, because in reality, this is a component of all the computations that you have to do in a propulsion system. It's a very easy, straightforward component. So any questions on this? We're good? Turned out easier than what we thought? Alright, so again, don't worry about the grade. It's distributed evenly and you get quite a bit of credits throughout, so should be okay. As I said, it's only 50% of the total grade. That
Leo.
is actually higher.
Leo, where the fuck are you, Leo? You missed a quiz, bro.
Alright.
Fucked up, fucked up.
So hopefully, I think the TA is working on grading it and we're supposed to.
We're having too much fun with this shit.
And also,
Can't even text my bitch.
keep in mind that
You can
there's a
text
lot
him
of opportunities for
permits.
bonuses. Each homework you're getting a lot of bonuses. Leverage those. You know, things of that nature. You will have those opportunities for in general. So don't worry really about your grade. I'm more interested in you learning this material primarily because you're gonna go out there and they're gonna ask you who taught you propulsion. And try to make you proud. Because propulsion field is not that big, so they know. And I'm doing a lot of propulsion, so it's not that I stopped. With a lot of connections with Pratt, GE, and Air Force, and so forth. So, meaning that you gotta make me proud. Okay? Alright, so we are wrapping up high-speed aero. The last component that we really have to do for high-speed aero is primarily seating nozzles. That's the last thing that we have to do, which we kind of did in some form, but not really spent a good amount on yet. But let's go over it because that's a critical component that we need for propulsion systems. And once we finish the seating nozzles today, that primarily becomes your you're ready for propulsion, which right after spring break that Tuesday we'll get into the propulsion systems, our first propulsion system. Okay, so let's talk about converging diverging nozzles. And simply, this is a review. We already sort of went over the equations of it, but just revisiting converging divergent nozzle in terms of how we solve it and do an example problem and so forth. So we already know the contour of the converging divergent nozzle right here. And we know that the area here is changing
Can you move your head?
relative to x to a converging section and diverging right here relative to x as a that diffuser-like form. The flow is isentropic unless I get a shock in there.
Okay.
And there's no heat transfer and no work being done. And we're going to assume frictionless. So we apply conservation of mass since it's no work, no heat, so I don't have to worry about the energy equation right here, but I could potentially get a shock, and we already know our shock, but conservation laws. And we drove it before, and we said, well, conservation of mass is really d rho over rho plus dA over A plus du over u is equal to 0, and conservation of momentum is equal to u du dx plus 1/2 dt dx is equal to 0, which is my conservation equations that we've been using so far. And from those, we drove the critical equation, which is area, area to, you already have it in the notes in the past, m2 over m1
Already started.
multiplied by